Good morning, everybody. It's good to see you all on a Saturday morning. Welcome to class. To those of you who are visiting, and it looks like we have a few visitors in here, welcome. I appreciate your willingness to be here on a Saturday morning and to spend some time doing some geometry with us. My name is John Tower. Just to quickly introduce myself, I have been a teacher here at St. Andrews for this is my 13th year, and this is one of my favorite courses to teach. I really love the geometry that we do here, and just the sort of the eye-opening experience that geometry can be to students. So welcome, and feel free to participate as much or as little as you'd like in today's lesson. We're going to try to give you sort of a feeling for what a normal class would be like. Obviously, the virtual class that we're doing today is a little different than our normal classroom. And we're going to try to replicate what we do as much as possible. We're going to start today's class by hearing from some students who have prepared some presentations on 4 problems that they've been working on recently that are also problems of importance for an assessment we're having early next week. So these problems are ones that they've looked at a couple of times and they've worked together with in a group setting, and they're going to be presenting them to each other for further extension questions, for sort of review for the quest that we're having next week, and just as practice in how to communicate the mathematics that we've been studying. So if you just give me 1 second to share the screen with the problems, we're going to start. To my students, could you please, if you're doing the presentation, could you please make sure that you read the problem so that everybody understands what the problem is. It will also be on the screen, and then you can take it away with your explanation. Okay, so Nikki and Olivia, you guys are up.
Okay, so this problem gave us Alex the geologist and said that he was 10 kilometers from a road and 45 kilometers from the base camp that he wanted to get back to. And it said that on the road, Alex can go 50 kilometers per hour, and in the desert, he can only go 30. And so they just wanted us to find the fastest route back to camp and how long that would take. And so we started off by determining what X would be. And we said that we'd want him to go through the desert to the road and then back through the desert because we thought that would probably be the fastest. So we said that for the length that he would be on the road, it would be 45 minus 2x, because X would be the length that he didn't use the road because he would be on the desert. And so we wanted to somehow use the equation for time, which is distance over rate. And so we said to find the distances that he would be on the desert, because that forms a right triangle, we can use the Pythagorean theorem. And so we said that it would be root 100 plus x squared, because one side is 10 and the other side is x. And so we know that he does that twice. And then for the road, we would just do 45 minus 2x, because we know that the full length is 45. And then we just subtracted the distance that he wouldn't use. And so then we use the equation time equals distance over rate. And for the first rate, we use the equation we found for the desert, which is root 100 plus x squared. And we put that over 30 because that's the rate he would be on the road. And then for the other one, we did 45 minus 2x, which is what we found before. And we put that over 50 because that's the speed on the road. And so then we added those together. But we just plugged that equation into Desmos and it gave us the line in the picture below. And it gave us the 0.7.5, 1.433. And so because we labeled X as the distance, we knew that the time, or Y, would be the Y value. And so we said that his time for the fastest route would be 1.433 hours, or 85.98 minutes.
Okay, great. So did everybody sort of follow that? That was really nicely done, Olivia. Thank you. So I think a couple questions that I would have for the whole class. First of all, how do you know there's a symmetry here, right? How do you know that this blue triangle over here and this blue triangle over here are going to be of the same size? Because it looks like you use their lengths to be the same, right? The length of the hypotenuse of those triangles as the square root of 100 plus x squared. So it doesn't have to be Olivia, but can somebody sort of give me a reason why that would be true?
Because it's looking for the fastest possible way for Alex to get from one point to another. If we just say the halfway point, and since the A and B both start 10 miles above, the fastest way to get to the center will always be along the same triangle, because they're both equal distance from the road, and that if you split the road in 45 into 2, then it'll still be the fastest point to 22.5. And if we just do that twice, it's still going to end up in the same space.
Good. Yes, exactly. Thank you, Kazan. So we all agree with that, I hope, that the fastest point, or the fastest time to get to that yellow point that I've marked there in the figure, is going to be duplicated on the other side of the figure, right? So we don't have to worry about the triangles being of different size. The other thing that I would just be cautious of if I were you guys is the only other route that really might make sense for Alex to take, that's not some subset of the routes that Olivia talked about, is to drive along the green arrow here, right? Directly from A to B. And I think you should probably check that this does not take a shorter time than the 1.433 hours that we found, right? So that should be an easy check, right? The time to stay completely in the desert is what? The 45 kilometers divided by 30 kilometers per hour. And that is 1.5 hours. So I don't think that that is actually a better path, but it's not off by much. So I think you should be considering, as you do these problems, what else could happen. Okay, any other questions on this one? Everybody feel good about this? Yeah, I think that's probably likely on your assessment on Monday, that there's going to be some variation of this problem. Probably not the same problem, but some variation of it would be pretty likely. All right, let's hear about this next problem.
So for problem 359, we were supposed to prove that the sum of angles in any quadrilateral was 360 degrees, and it asks us about 3 other triangle polygons. So for the quadrilateral, we started out by putting different examples and trying to see what could work to prove it, and then we realized that they could all be divided into like 2 triangles, like the smallest amount of triangles would be 2. And if there were 2 triangles, then it would be double the angle measure. So it would be 360 degrees. And then we use the same method when finding a pentagon, a hexagon, and a 57-sided polygon. And we realized that there was a pattern where with the triangles, like the number of sides -2 times 180 would give the angle measure. So we use it to find the 57-sided polygon, where we did 57 minus 2 times 180 would give the angle measure, which was 9,900 degrees.
Good. Nicely done, Angela. So did everybody follow the sort of the big idea that Angela's talking about here is that, and I think this is a really nice way of starting this problem, right? Is looking at specific types of quadrilaterals, right? The rectangle, the rhombus, the kite, seeing if it works for these very specific types of shapes, and then trying to expand that out to the much more general quadrilateral, right? We want to show that this works regardless of what kind of shape we have. And I think, Angela, correct me if I'm wrong, what you said is that regardless of what type of quadrilateral there is, it can be split into two triangles.
Yes.
Right, by constructing a line from one of the vertices to the opposite vertice. And if that's the case, and I label the angles something like this, what do the measures of angle 1 plus angle 2 plus angle 3 add to?
180 degrees.
180. And 4 plus 5 plus 6 also add to 180, right? But the sum of all 6 of those angles adds to the interior angle sum of the quadrilateral. And so if 3 of them add to 180 and the other 3 add to 180, then combined, they all add to 360 degrees. Yeah, and then it looks like down here in the bottom, it looks to me like what you've said now is, well, we can do the same thing with a pentagon. We can take any pentagon and split it into 3 triangles, and any hexagon and split it into 4 triangles, and any 57gon that we drew, which is quite an undertaking if you try to draw the 57gon, can be split into 55 triangles. All of which, those 55 triangles, all of which have an interior angle sum of 180 degrees. And so 55 times 180 would be the answer. So I think, could we say this as sort of like a definition, or maybe even a theorem, if we try to prove this, that the interior angle sum of any n-gon is n minus 2 times 180. I think this is what you were getting at, Angela. Okay, does that seem reasonable to everybody? Questions about that? All right, great. So let's move on to the next problem.
So this problem asked us to sketch a rectangular box that has one corner at A, which is 0, 0, 0, and adjacent corners at 12, 0, 0, 0, 4, 0, and 0, 0, 3. So the first thing that we did was we drew the picture. So we sketched out everything. And we knew once we found A, which was 0, 0, 0, the origin, that we had to find the one that was farthest away from that for G. So since A was at the bottom left-hand corner, we knew that G had to be at the top right-hand corner. And what we did after that is we knew that in order to get from A to G to create that point, we would have to use the X coordinate for B, which was 12, because that would bring us 12 down the X axis, and then 4 to get us to F, and then 3 that would get us to G, because all the other coordinates were zeros for the other points, so it obviously wouldn't get you anywhere if you used those. So we found that G was 12, 4, 3. And then the problem asked us to find coordinates for P, which is the point on segment AG that is 5 units from A. So what we first did was we found the distance between A and G, and the way that we did that was we did the square root of 12 squared plus 4 squared plus 3 squared, because that's the vector, and we got a distance of 13. So in order to find 5 units away, you have to change the vector to work with 5 units. So we divided 13 by 5 and got 2.6, and divided our entire vector by 2.6, which gave us the new vector 4.61 comma 1.53 comma 1.15. And that's obviously the point, but if you want to check your work, you can show that adding that vector to the origin is going to get the point P.
Okay, good. Yeah, I think somehow I managed to cut off some of your work here. I'm sorry, I apologize about that. But does everybody sort of follow the idea here? Right? We want to find, in this 3-dimensional picture, we want to find this point. I'm putting it in here. It's this blue point like P that's 5 units away from A. So there's a vector from A to P that's 5 units long, and the vector from A to G is 13 units long. So I think what I heard you say, Eleanor, was this, that P, if you start at point A, which was 0, 0, 0, and you add into it 5/13 of the vector 12, 4, 3, then that would take you to the position that you get. Am I paraphrasing what you said correctly?
Yeah, no,
Yeah.
that's correct.
Yeah. Okay. So how does everybody else feel about that? Good. Right. So this would be what, 60/13, 20/13, and 15/13. All right. Questions on these? Are we getting better at drawing these pictures? Everyone? Darden shaking her head no, it looks like. Okay, just keep with it. I know that this is drawing these 3-dimensional figures in a 2-dimensional page is tough, but keep with it. You'll get there. All right, let's hear the last one, which was a angle problem.
So 361, we were told to find like there's angles that were marked with a variable, and we were told to find those angles. And for the first figure, it's angle X, which is like the top left angle. And so what we started by doing was taking this 38 we were given in the bottom left corner, and we knew that it would, because of like opposite, like it would be the same as the top right angle that you can see there. It's like opposite.
This one?
Yeah, that one.
Okay.
And because
Is there a
yes.
reason, Gibson, why those are?
It's is it opposite interior angles?
Yeah, we usually call it alternate interior.
Alternate, yeah.
And what makes them the same? What about the figure makes those two the same? Because not all alternate interior angles are equal.
Yeah, they're the same because the horizontal line on the top and the horizontal line on the bottom are parallel.
Okay, yes, right. And they're cut by the same line, right? The same transversal line?
Yes.
Good.
And so we also knew that with this angle of 71 we were given, that because of a construction we made towards that angle 38 up at the top, that made it like continued that line, that the angle adjacent to it would be 109 degrees, because that's the definition of a straight angle, adding up to 180 degrees. Yeah. And so then we just added the 38 and 109 and used that to find X, which was 38 degrees. Oh, no,
33, right?
33 degrees. Yeah.
Yeah,
So
let's
for this, yeah, the second one was a little more tricky. So we were told to find angle W, which was the top left angle, and angle U, which is like bottom right. It's kind of hard to see. And so what we did first was we knew that there was a 72 next to angle W, and they're
instead of next to, what's a better word for that?
adjacent.
Adjacent to, yes, good.
Adjacent to angle W, and since they share a parallel line, they share two parallel lines actually. We knew that angle W was going to be that there's the angle supplementary to angle W would be 72. And so we did 180 minus 72 to find W, and it was 108 degrees. For angle U, we made looks like Margaret did it differently than I did, but we continued one of the like upward angling parallel lines to make a construction. Like you can kind of see that down there, and we knew that 70 we had the 72 at the top already, and because of alternate interior angles, we would also have a 72 in this new triangle down at the bottom. And we also had 82 because we were given 98 degrees. And we knew because of the definition of a straight angle, it would be 82 degrees for that other angle. And then since we had those two, we could find the last angle. Sorry, my roommate's talking.
Sorry. Okay, did everybody follow that? That this 72 and this 72 down here are also alternate interior angles, right? And found that this 82 right here is a what kind of angle? What do we call that with the other 82? So these two 82s are
Vertical angles.
vertical angles. Yes, thank you. So that leaves us with this triangle right here, and that U has to add, U plus 82 plus 72 has to add to 180. And so we get 26 for you. Yes, good. That seem okay to everybody? Are there any questions on any of these problems? I would say that these ones are pretty important, big picture type problems for our test for next week. Okay, for those of you that are visiting, this is sort of an example of the type of work we've been doing, right? That you can see that we're not focusing on any one type of specific problem. We don't have a section that just deals with angle measures, and we don't have a section that just deals with 3D figuring. We're doing all of this stuff concurrently. And so, this is the for some of the students, the frustration and headache, but I think this is a better way of working through math. I think you're going to retain more of the mathematics if you're doing it this way. All right, so with the rest of the class period, I want to take a few questions that you guys might have, my students might have about the upcoming test. So the floor is open to whatever you guys would like to ask about. I'm going to try to share the actual problem with everyone so we know what we're working on, and then we'll do a quick work to get through it. Okay, so the floor is open for your review questions.
Could you go over 358 for me, please, sir?
358. All right. So let me get to that one. All right. So 358 says find an equation that says some point xy is equidistant from f, which is 2, 0, and the y-axis. Plot 4 points that fit this equation. This configuration of all such points is called a parabola, right? So that's an idea we already know, right? The parabola is the set of points that are equidistant from a fixed point and a fixed line. They call the fixed point f. What's the reason for that? Do we know the name of that? What we call that point? It's called a focus point. Does that sound familiar? A focus point, and the y-axis here is called the directrix line. All right, so let's take and see if we can do this. So I'm just going to move over here so I have a place to write. So we said there is a point at 2, 0, which might be over here somewhere. And there is a vertical line along the y-axis. And we want to find all the points that are equidistant from both. So this blue point is an example of a point that's equidistant from both. This blue point might also be equidistant from both because that distance and that distance are the same. There might be another one over here, right, where this distance and this distance are the same. And et cetera, you can keep drawing in these points. And so we start to get a curve that looks something like this. And there's points down here as well, right, that make this true. And this is called the parabola. Okay, so far so good? All right. So let's take this blue point, this one right here that I'm marking really big, and let's call that our XY point that we're looking for. What would this white point over here's coordinates be? The one on the y-axis, if I had to give that some coordinate points.
0y.
Yeah, right. It's x value 0, and its y value is the same as the y value of the blue point. So what is that total distance from 0y to xy? What would you call that? So I'm talking about this distance here.
Would that distance just be x?
Yeah, it's just x, right? It's a horizontal distance from 0 to x, so it has the length of x. This distance right here, although this line looks like it's vertical, it's not necessarily vertical, so I don't want to assume anything here. This distance over here, though, I could find using the distance formula. So how do you like this if I write y squared plus x minus 2 squared? Does that seem reasonable? Everybody with me here following along? Yeah? Okay, so those two distances are supposed to be equal. X equals the square root of y squared plus x minus 2 squared. All right, this is an equation. The one thing I don't really love about it is that there's X's and Y's on the same side of the equation. So I think from here, we're either going to want to solve this for X or solve it for Y. So let me do the algebra sort of quickly. I think that this is not the thing that people are having trouble with. So if I squared both sides, I would get X squared equals Y squared plus X minus 2 squared. And if I FOILed out the X minus 2 squared, X squared minus 4X plus 4. Does that look okay? The X squared on both sides of the equation cancels. And if I subtract Y squared over, or actually I'll subtract the X's over. So I get 4X minus 4. And then if I take the square root of both sides, I get Y is plus or minus the square root of 4X minus 4. So there's a equation for the parabola. And I can find those 4 points that they asked me to plot by just putting in any X value I want in there. Sorry, any X value greater than 1 there, I guess. Okay, how's that look? Everybody, any other questions on this? I think this is a good problem. I like this parabola idea. All right, what else?
Can we go over 350?
350. Just turn to my page, my notes here. Yeah, okay, great. So 350, let's take a close look at that one. If ABC is any triangle and TAC is one of the exterior angles, then what can be said about the size of angle TAC in relation to the angles, the other angles in the figure? All right, so this was a really important result for us. And I think that this is definitely something you're going to have to use next week on the assessment. So we got something like this, right? We've got whoops. Sorry, make it so everyone can see. Let me even draw a better picture than that. I'm gonna draw a bigger picture. So we've got a triangle here, and it says, let me just get that again. So this is A, B, C. And somewhere up here, there's an angle T. Oops, I've got these labeled wrong. Sorry about that. So this one's C and this one's A. So angle TAC, I'm going to call it angle 4. I'm going to call this 3. I'll call this 2, and I'll call this 1. And it says, what do we know about angle 4 in relation to the other angles? Angles 1, angles 2, and angle 3. So somebody want to give me an idea here? Like what do we know, or what can we show?
We know that angles 1, 2, and 3 have to add up to 180 degrees.
That's a great start, right? So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180 degrees. Okay.
And another thing, isn't angle 1 and angle 2 equal to, I think, angle 4?
I think that's what we're trying to show. Yeah.
Oh, okay. Yeah,
I think that's the result that we're after.
okay.
Tamia, can you tell me how you might actually get there from what
Okay.
we got started?
All right. So we know that angle 1, angle 2, and angle 3 is 180, but we also know that angle 3 and angle 4 would also equal to 180, and that's because, is it because they're vertical angles or
They're
alternate?
not vertical. What are they?
Well, angle 4 is the exterior angle of angle 3, and with that, the interior and exterior angles will always add up to 180.
Yeah, that's a good reason.
Yeah,
The other reason you could say is they form a straight angle,
yeah,
right? So either one of those reasons is fine.
okay.
All right, so now both of these things are equal to 180. So what can I do with that?
Well, since we could see that we could substitute angle 1 and angle 2 for angle 4 because they both equal 180, but so yeah, so angle 1 and angle 2, that gave me the idea that angle 1 and angle 2 is equal to angle 4.
All right, so let's see what we got here, right? So I think what you're saying is this. They're both equal to 180, both sums.
Mm-hmm.
So they have to be equal to one another.
Yeah.
And since the measure of angle 3 shows up in both sides of the equation, I could subtract it out. Right? The only way that this is a true statement now is if these two things and this thing are equal. Everybody follow that thinking? So the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2. And that leads us to this result. That the exterior angle measure of a triangle is the sum of the two non-adjacent, right? Because the adjacent is angle 3. Interior angle measures. Of the triangle. And that's always true, right? It doesn't matter. We can change this picture to make the triangle equilateral or isosceles or more of an obtuse triangle or whatever. But we can still make this same argument regardless of what the triangle looks like. All right, good. So this result is a really important one, and we've used it in a lot of our proofs moving forward from here. All right, good. We probably have time for one more question. Is Justin here? I know, Justin, you emailed me. You said you had some questions. Or do you have anything you want to talk about?
I just wanted to go over, I think it was 307? No,
307.
sorry, it was 309.
Yeah, okay. So let's take a minute and go back to 309. So that one is here, right? There's a point at 0, 1. It's reflected across a line. 2x plus 3y equals 6. Find coordinates for its image. All right, so let me see if I can draw that for us. So we've got a point at 0, 1. We know that's here on the y-axis. The line we were given that's the reflection line is 2x plus 3y equals 6. If I put that into slope-intercept form, maybe I'll see a little clearer what that line looks like. So negative 2/3 x plus 2, I think. So the line of reflection is looking something like this. All right, so tell me some things about the image point. Like, where would you roughly put it? Again, how would you know where to roughly put it?
Like it would be perpendicular to the line 2x plus y3 equals 6, and it would like be like the same distance from 0.0, 1 to that line, but on the other side.
Good. All right. So it's on the perpendicular, which is this dashed line I put through, and it's equidistant from this yellow point, right? So the white point here is the image point. So maybe if we could find this vector and the yellow point, then we could start at the yellow point and add in the blue vector to get to the white point. How's that, at least for an idea of what to try? Sounds good? Yeah? All right, so how am I going to find the yellow point? What do I need to know first?
You can make a line with the 0.01 with the opposite reciprocal slope of the original line and
Okay.
find the intersection.
Yeah, good, right? So we can write the equation of this line right here, which is what? Y minus 1 equals 3/2 x, or y equals 3/2 x plus 1. And now how am I going to find the yellow point once I know that line?
Set the lines equal to each other.
Yeah, set these two equal, right? And solve the system. So 3/2 x plus 1 has to equal negative 2/3 x plus 2. And probably multiply through by 6. I'm going to do this fairly quickly because we're running a little, whoops, sorry, that'd be 9, right? Uh, 9x plus 6, if I multiply through by 6, and this would be what? Minus 4x plus 12. So 13 x's equals 6. X equals 6/13. That's the x coordinate of the yellow point. And the y component can be found by plugging into the others, you know, whatever it might be. Guess I got to multiply it by 3/2 and add 1 would be 18, 26, I think 44, 26. All right, I think we're going to run out of time, but does everybody sort of see how to finish from here? Right, Justin, are you okay to finish from here? That now it's fairly easy to find this blue vector, the one from 0, 1 to the yellow point. and then take that vector and add it to the yellow point. And that'll take you up to the white point, which I will tell you, because I have the answer here, if you want to check it, 12/13, 31/13 should be the value of the image point. Okay, so just a couple last thoughts. First off, I want to make sure that everybody feels like they're in fairly good shape for next week's on Monday's assessment. If you're not, if you're feeling like you need extra help or there was something today that you didn't understand, please reach out to me. I was thinking Sunday night might be a time that we could, get together on Zoom and talk about any last minute questions you might have. To those of you that are visiting today, thank you for spending your first 50 minutes this morning with us. If you were here with us in our classroom, you would see a little bit more interactive work with groups. We spend a lot of time sort of brainstorming problems in small groups. We spend a lot of time sort of testing our ideas out with each other, with our peers before you're sort of put on the spot. Like those presentations you heard today weren't just one person working alone. They were a group effort to get a problem ready to present to the class. And those were the result of probably looking at those specific problems at least 2 times, but in some cases, probably a third look for some people at those specific problems. So, so I guess that's it for today. Again, let me know if you have any questions, and to the rest of you, the visitors, I hope you enjoy some other classes this morning. And I think Tuesday is also a day where you can come in and visit some classes if you'd like. So it was great having you with us, and best of luck with your decision making.
Thank you.
All right, you're welcome.